In our previous video, we found our regression model for our data set here, where we have these vehicles named Sparta, and we are looking at the age of Sparta and whether or not we could predict the repair cost. So in our previous videos, we looked at how age and repair cost are correlated. They have a positive correlation. And then we created a regression model, and that regression model we came up with y hat. So repair cost is what we're trying to predict. Age is our x value. And so then our formula, which is b naught plus b1 times x, we found that the intercept is 77.41. So if there was no age, brand new car, the repair cost would be $77. Plus, as the age increases, the cost increases, and it increases at a rate of 57.43 times x. So what we looked at in our previous video is that if, for example, the car was 4 years old, we would take 57.43 times 4 and add 77.41, and we did that, and we got 307.10. Now, we end up with that regression equation whether we use the data analysis tool pack in Excel and pulled the coefficients here from the table. That gave us this formula. Or whether we did it in Python. And then we can see here 77.5, 57.4. They both give us the formula. They both also tell us that the R squared is 92%, so 92% of the variability in repair cost is explained by age. So we have a well-fitting model. And we also looked at the 95% confidence intervals for both the intercept and the x variable, the independent variable. And since they both are not spanning zero, so there's no zero in between the lower bound and the upper bound, these have a statistically significant impact on the repair cost. And you can see the small p-values as well tell you, if we compare the p-value to alpha, a p-value less than alpha tells us that it is different than zero, and so both the intercept and age are statistically significant in predicting repair costs. So that's what we looked at in our previous video. What we want to do now is talk about the idea of, let me just go back here, talk about the idea of standard error of the estimate. The standard error of the estimate is a measure of dispersion or variability between the observed values, y, the repair costs, and the regression line. So what we're looking at is how far away is that line of best fit and the predicted values, so y hat, from the actual values of y. Okay? Now, standard error is what we're focusing on here. And standard error is the sum of the differences between the actual values of y minus the predicted values of y. That's the part we're looking at here. So actual minus predicted, squaring that difference, and dividing by n minus 2. Okay, so we're getting our standard error. Our standard error is related to the correlation. You can see here that standard error is equal to the standard deviation times the square root of 1 minus r squared. Okay. So how much variability we're going to have is going to depend on how strong that correlation is. For example, if we have a perfect, linear, positive correlation, then when you go to do your line of best fit, it's going to be right on top of that data. So our R would be 1. 1 minus r squared would be 0. And there's going to be no error because you're right on the dots. So the stronger the correlation, the closer that correlation coefficient is to 1, the smaller the standard error. So there's this relationship between standard error of the estimate and the correlation coefficient. Now I'm just going to zoom in a bit. So here is our forecasted line. What we assume is that the actual y's follow a normal distribution where the center of the normal distribution is on that line of best fit. So that brings us back to discussions we've had about normality before, right? So we assume that the standard error of the estimates is approximately normal. So here we have our line of best fit going through. As I said, here is the line of best fit, and we're assuming a standard normal distribution in terms of the scatter of the actual values away from the line of best fit. Now remember, the whole point of this line of best fit is it is the line of best fit because it is the point at which it's closest to most of the actual values, which then makes sense that most of the values would be near that regression point. And so we can use the empirical rule, right? So 1 standard deviation, 2 standard deviations, 3 standard deviations. Our regression line goes through here, right through the middle, and most of the actual data should be within 1 standard deviation of that regression line. And in fact, that's 68% of the data. And then 2 standard deviations should be about 95%. 95% of the data. And 3 standard deviations should be 99.7% of the data. This is that empirical rule that I keep bringing up. Okay. So we're talking about how far away when we are plus or minus 1 standard deviation, 2 standard deviations, 3 standard deviations. Okay. So we can make the same type of statement about our regression. And so because we have this distribution here of these are the actual y's around that y hat value, because it has that normal distribution, we can then use it to create confidence intervals around specific values. So we could look at what, with 95% confidence, a 4-year-old vehicle will cost what? So not only do we just give the point estimate, which we did just a moment ago as I figure out where we were, where I talked about how a 4-year-old vehicle would cost 307, but we can also give a confidence interval around that 307 by the fact that the standard error of the estimates has this normal distribution. We can start treating it like a sampling distribution and do confidence intervals, which is where we want to go next in our discussion. So we interpret the regression equation, right? We got the equation. It told us that the underlying cost for a a brand new vehicle is $77.41. And then as you increase the age of the vehicle, each year costs $57.47 more than the year before. And we plugged into our equation and found that the 4-year-old vehicle would be expected to cost $307. So that's where we've been so far. Now, if we calculate the standard error of the estimate, we can then use that standard error to create these hypotheses. Okay, so generally, how would you calculate the standard error of an estimate? You would compare the predicted, that's the y hat, to the actual cost y, so y minus y hat, find the residual, square it, divide it by n minus 2, and take the square root. Okay, and then in this case, the standard error of the estimate is 26.5. Well, that sounds like a lot of work. So how could I find the standard error of the estimate, this 26.5, from Excel or from Python? If we are in Excel, for the output, go and find the sum of the squares of the residual. The sum of the squares of the residual you see here is 5618.9. We take 5618.9 56, 8, start over. 56, 18.9. That was the sum of the squares of the residual. We then divided by n minus 2, which is going to be 10 observations minus 2, and then take the square root of that. So if I go back into Excel, if I have this number here, I'll just highlight it so we can see it there. I'm going to take this number divided by the observations, which is 10 minus 2. There's the right buttons. Okay, and then I'm going to take the square root of that. And so what I have found is that the standard error of the estimate is 26.5. Standard error of the estimate equals 26.5. So if you can find the sum of squares of the residual, divide by the observations minus 2, take the square root, you have the standard error of the estimates. If you are in Python, you don't get that information in this initial summary that we have here. So instead what we do is we do an ANOVA. So this ANOVA is going to use statsmodels.api as SM, so we make sure we import that. If you did not see our previous regression video, please go back and look at that so that you make sure you know how to get access to this workbook and the file that goes with it in the first part of this discussion here so that you can run this code. Okay, we won't go through it again because you're probably getting tired of hearing it. All right, so we need this statsmodel.api as SM. When you have run that, then what we can do is we can take this OLS underscore reg, which was our ordinary least squares regression we ran in our last video, and we can take the output from that and use it to create an ANOVA, an analysis of variance. So we are going to do an analysis of variance. Run this, and that's because we need the sum of squares residual 5618.9. That's that same sum of squares residual that you saw in the Excel output. We simply have to ask for this additional information using this ANOVA underscore LM from sm.stats, and you need to have already created your regression model and given it a name. So we created this OLS underscore reg as our regression model, and that one was using the statsmodels.formula.api as SMF. So once we have that, we now have this 5618.9, and we have our 10 observations. We take 5618.9 divided by 10 minus 2 and take the square root. We get the standard error of the estimate. Well, why go through all of this work? What are we trying to do with this? Well, ultimately, because the standard error of the estimate can be treated like a sampling distribution, we can create a confidence interval around a particular year to get the cost, not just a point estimate, but a range. So I'm going to take us back here to the theory because we need two pieces. We need this formula right here. So the confidence intervals for the mean value of y hat for a given value of x. So when we're doing confidence intervals previously, we said, okay, the mean in the population is between these two. Here, we want to know for a particular point on the regression line, what is the confidence interval for that? So for a given value of x, like the vehicle is 4 years old, what is the range of costs? So what is the expected value for y, which is the repair cost? To do that, we will do our point estimate, which is going to come from that regression line. That's the line of best fit piece, which in our calculation, that's where we used y hat equals b naught plus b1x. And we found that for a 4-year-old vehicle, that was $307. Okay, then we do plus or minus. We have two sides to this confidence interval. We are going to need a critical value that is going to come from the t-distribution. Then we are going to need a covariance. Sorry, covariance SYX. No, sorry, that's the where the standard error is going to go. Sorry. Bleh. Take that back. Brain fart. That's the whole reason we did this. Standard error of the estimate was to get this piece. Then we're going to need to find the square root of 1 over n plus, and then this x minus x bar is going to be, for our 4-year-old vehicle, how it compares to the average age of the vehicles. Okay, so we're going to need x minus x bar squared and the sum of x minus x bars squared. So this formula is important to capture for doing these types of intervals. So let's look at how this works. All right. On paper, the way this works is that we are going to take our 307.13 and then we need a t-value. Remember that t-value is going to depend on alpha. So if this is a 95% confidence interval, and then it's also going to depend on our degrees of freedom. And it is an n minus 2 degrees of freedom here. Okay, so let's figure out where that came from. Well, we can go equals t inverse. And the probability here, it's two-sided. We want 0.975. And our degrees of freedom are going to be n minus 2, so it's going to be 8. We get 2.306. So that's where this 2.306 came from. It's an alpha of 0.05, but because it's two-sided, we divide that by 2, and then our degrees of freedom are n minus 2. Okay. Then we have that 26.5. This is the standard error that you just calculated. And then we need our 1 over n, okay? And then we need this piece here, which was x minus, x minus x bar squared divided by the sum of x minus x bar squared. That's this last piece right there. So let's talk about how we would get that from the data. So we could, if we were doing this by hand, we could take all these values of x's and we could find the average value of those x's and subtract it and then square it and add them all together, and that would give us this pot on the bottom, this 20. And for the particular one we're looking at, the x is 4 years, we compare that to the average of 3, and we square that to get this formula. Well, you probably don't want to do all this work, so how could you get this information? Well, in Excel, what we would need, so this is our, I'm just going to write this out, this is our critical value. We have our standard error of the estimate. What we would do is we would take our, first we got to find the average for x's. So if we go back to the original data, equals average, gives us that 3, okay? And the other thing that we can do to find, that'll give us the 3 to do this 4 minus 3 squared. But to find this bottom part, one way we can find this bottom number without doing all these steps is to recognize that the standard deviation, if you recall, what was the formula for standard deviation? It's the square root of the sum of some variable like x minus the average x bar squared divided by n minus 1. which means if we want to solve for the sum of x minus x bar, if we want the sum of x minus x bar squared, what we do is we get rid of the square root by squaring the other side, and then we multiply that times n minus 1. So this formula here rearranges for that, which means if I have the standard deviation, the sample standard deviation sample, make sure you do that one because that's the n minus 1. This is just divide by n. If I do that and then find the age, I get 1.49. So that's S. This is x bar. And if I want the sum of square x, sum of square x, not z, sum of square x, then what I do is I take standard deviation, square it, turn it into a variance, multiply it times n minus 1, which in this case is 10 minus 1, and we get 20. Okay, so that's where that comes from. So I have x bar, I have sum of squares. If I go back to my formula, I can find this confidence interval. It is going to be, let's see if I can put these on the screen at the same time. Okay, we're going to take our 307. That is our calculation. 307, actually, let's just do equals. It's this here, right? That's the point estimate in our confidence interval, point estimate. Okay, and then we want to do equals, and that's going to be our critical value times our standard error of the estimate times the square root of, and that's 1 divided by n, which is that observation there, plus, and then what we need in our formula, x minus x bar squared. Maybe I'll just do this in pieces. It's too hard to do all this laid out. Let's do this first part. X minus x bar squared equals x, which is 4, minus 3. Put that in parentheses, square that. That's that top part of the formula that you see right here. X minus x bar squared. Okay. X minus x bar squared is that number there. Then we're going to take that number and we're going to divide it by the sum of squared x. That's the bottom of the formula. That sum of squared x we just figured out was 20, and that was on my other tab. So you can actually see it right here. Sum of squared x is 20. Okay. And so now I have this part. So just to do this, I'm going to do the square root of 1 divided by 10 plus I am going to add all of this, which is the part that's hidden there. All of that lives under the square root. So now I'm going to take that and I am going to do my critical value times my standard error times the number I just calculated. Do I have a number there, or is that something else? It seems like it's just times this. Oh, it's because I stupidly wrote this out as if it was like just a whole statement. Let's do standard error of estimate 26.5. All right, so this should be critical value times standard error of the estimate times our calculation there. I get 23.67. And then I'm going to take my point estimate and I am going to figure out where I'm going to put this. Equals point estimate minus that and point estimate plus that. Okay, so what is this saying here? This is saying I've created a confidence interval for those with 4-year-old Spartas. Their cost is going to be between 283 and 330. Okay, so we went through all that. So that's why this particular formula, because no one really does this in any of the software, I'm just going to clean this up so you can see it nicely, is an important formula to have. So that's the standard error. This is our critical value, and we can get this part of the formula, this sum squared of x, by taking your standard deviation squared times n minus 1. Okay, which you can't see because my face is covering that up. So here we can get the confidence interval for a particular value of x. So the age of the Sparta is 4, and we have found then that in this case, the repair cost ranges from 283 to 330. Okay. If you are in Python, we have these pieces that we need to do this. We've already calculated that 307 cost from our intercept and our slope and our intercept here. And then to do the rest of that, we will need our critical value for t. We will also need the standard deviation for x. So if you do this additional line of code here, which is stats.descriptive_stats.describe, and apply it to your table, you get the descriptive statistics for both x and y. And that'll give us the mean, the fact that the average x was 3, and that the standard, or where'd it go? Why have I lost it? I'm looking for the standard deviation, and I'm just not seeing it. Losing my mind. Standard deviation. There we go. 1.49. So the standard deviation is there. So again, when you have the standard deviation, square it times n minus 1. Well, n is 10, so times 9. That will give you that sum of squares x. We can take our 4-year age Sparta, subtract the average for 3, square it. That'll give us the top part of this formula. So you have all these pieces here. To get the critical value in Python, we can have Python give us that information as well. So in Python, we need to do this. Where did this go? We need here. We're going to use from skippy.special, we're going to import std trit. And so we are using the t distribution, the inverse of the t distribution. When you do that, so if I do std rit, then what you need for that is first your degrees of freedom. So here our n minus 2 is our degrees of freedom, so 8. And then just like with the other, when we do our inverse, it's everything to the left. If this is a two-tailed confidence interval, right, then we are going to type in 975 because half of the 0.05 goes on one side, half goes on the other. And when we do that, all right, I'm missing a letter here, std trit. There we go. We get 2.306, and if we go back to what we found in our Excel, 2.306. So you can get critical values in Python as well when you're having to do some of this stuff by hand, because even Python doesn't automatically do some of these things. Now, we had, in that scenario, let's go back. We had looked at the confidence interval for the mean value of y hat for a given value of x. And we used this formula, and we had to do it by hand, whether we're Excel or Python, to get that summary. One other important formula that we will go through right now is the prediction intervals for an individual value of y hat for a given value of x. So this was a confidence interval for an existing value of x and the y hat. This is a prediction interval for an individual value of y hat for a given value of x. Notice that this formula looks the same as the other formula. Can't quite see them both on the table at the same time, with the exception of there's an additional 1 here. Okay, so we could do our same process that we just did, pulling these pieces from our data analysis tool pack in Excel or from calling more information, ANOVA's descriptive statistics in Python. But to find the predictive interval for an individual value, we're simply just adding a 1 into this formula. What this gives you is that if we wanted a 95% prediction interval for the repair costs for Mrs. Paul's 4-year-old Sparta. So here we're talking about a particular person, whereas in the previous one, we were looking at the average repair costs for all 4-year-old Spartas. So it was more general. Here we are looking at predicting an interval for a specific person. So we're making this additional adjustment here because of that specific individual and not the average. Okay, so you're allowing for a bit more variability because you're looking for, instead of having it be an average value, instead of an average value, we're looking at the individual value, so there's more variability from it because it's not just the center, but it can be out a little bit more. So in this case, same procedure. Point estimate comes from our y hat, right? So we calculated this y hat equals, and it was 77 plus 50 something. 7741 plus 5743 times 4 gave us the 30710. Okay, that gave us our y hat. And then our 2.306 came from that t distribution, which we could get in Excel by doing t inverse. Okay, or we could do it in Python by doing from skippy.special import stdtrit to get that value. Okay. Then we had our 26.5, which was the standard error of the estimate. To find the standard error of the estimate, you'll remember we did. Okay. We needed our sum of squares for the residual divided by n minus 2. Sum of squares residual divided by n minus 2 square root. So we went in and we found the sum of squares for the residual in Excel, divided by n minus 2 and took the square root. Or in Python, we used the ANOVA to give us the sum of squares of the residual, divide by n minus 2 and take the square root. Then in our new formula, we'd do a square root of 1 plus 1 over the number of observations, here was 10, plus x minus x bar squared divided by the sum of squares for x. And again, this one you can find by taking the standard deviation squared times n minus 1. So you can get a prediction interval for a given person. You can get a confidence interval for an average value when you know x. So these are all ways to extrapolate and pull more information out of our regression, because our regression gives us a point estimate. Okay, our confidence intervals give us y hat is in between, or sorry, y hat plus. Let's just do this here. Maybe I'll just go back. See, where's my confidence interval? Oh, maybe that's it. So it gives you upper and lower bounds. So we take that point estimate and we add in some additional variability, whether it's for the average y hat for a given value of x, or whether we're predicting for a particular person by adding some additional variability for the fact that it's not just an average, but it's for a person in particular. So we can create these confidence intervals to get even more from our regression analysis.